So, this is the total energy of the transition of the electron from higher level to lower level in the form of radiation, and this is the wave number of the radiation or wave number of the photon emitted. And one thing is very important about the emission. When we pass this radiation emitted by the atom due to transition of the electron from higher level to lower level through a prism, because we know when we pass the light through prism we get the spectrum, and here we pass the radiation through prism, we will again get the spectrum, right. And this spectrum is called the emission spectrum, because we are getting due to the emission of the photon through atom. And this emission spectrum we observe certain lines, certain discrete lines, and these lines are called the spectral lines, and number of these spectral lines depends on the excited state and value of Z. So, let us now find the way to calculate the number of the spectral line due to transition of the electron from n equal to n to n equal to 1. Okay. And now we know the number of the spectral lines emitted when electron jump from excited level to lower level. Suppose this excited level is n equal to n, we can say nth level to ground level transition is happening. From n equal to n to n equal to 1, let us consider the number of the possibilities through which the electron can move. It can move from n equal to n equal to 1, from n to n minus 2, from n to n minus 3, and so on. We can say n to 3, n to 2, n to 1. That means these are the possible ways. That is from n to n minus 1, n to n minus 2, n to n minus 3, n to 3, n to 2, or finally n to 1. These are the possibilities while motion of the electron from excited level to ground level. Why we are considering? Because sample of the gas may have many atoms, and in certain atom the excitation de-excitation from n equal to 1, and there may be possibility for getting the radiation corresponding to n equal to n equal to 1. If we count these number of the possibilities, these are n minus 1 possibilities, that is n minus 1 transitions. Now, let us find the number of the possibilities when electron start moving from n equal to n minus 1, that is nth level, to n equal to 1, that is the ground level. Number of the possibilities will be, in place of n we can substitute n minus 1, here will be n minus 2, here n minus 1, here will be n minus 3, and like this, and finally n minus 1 to 1. And if we count here, there will be n minus 2 transitions, right. Similarly, now let us consider from n minus 2th level to n equal to 1 or ground level. So, here what we will do? We will substitute in place of n minus 2. So, transitions here will be n minus 2 to n minus 3, n minus 2 to n minus 4, and here from n minus 2 to 1. And if we count here, there will be n minus 3 transitions. And similarly, if we keep on doing like this, finally we will reach to n equal to 2 level. From n equal to 2 to n equal to 1, there is only one possibility. That means only one transition is possible. If we add these number of the transition, that is 1, 2, 3, n minus 3 plus n minus 2 plus n minus 1. So, let us add number of the possibilities now. This is 1 plus 2 plus 3 plus n minus 2 and n minus 1 finally, because final was n minus 1 here. And we can observe this is the arithmetic progression, and the summation of the arithmetical progression, we have the simple formula, and this formula is equal to n multiplication n minus 1 divided by 2. So, this is the final formula we can use for counting the number of the spectral lines. Suppose electron initially is at n equal to 4 and we want to calculate or we want to find the number of the spectral line. We write here in place of n, that is 4, and here is 4 multiplication 4 minus 1, that is 3 divided by 2. That means we will have 4 multiplication 3 divided by 2, that is equal to 6. That is the number of the transition or number of the spectral lines will be 6. So, this is the way to find the number of the spectral line in the emission spectra. So, up to this point we learn few important theoretical points. Now, we are going to move to the illustration section. In that section, we are going to take few important illustrations through which we are going to learn the application of the concept. So, let us move to the first illustration. In this illustration, it is given the potential energy of electron and proton at separation small r given by capital U equal to k log r, where k is a constant. For such hypothetical hydrogen atom, calculate the radius of nth Bohr's orbit and energy level. Right? First of all, let us analyze the situation. What is the situation? Really, here it is. You are given U equal to k log r, k is a constant and this log is natural log r, right? This is the potential energy relation between the electron and proton at separation small r. But while driving the formula for the nth Bohr's orbit and energy level, we use the relation, that is capital U equal to k ZE multiplication minus E divided by small r, that is equal to k minus k ZE square divided by small r. And we calculated the force between the electron and nucleus, that is equal to k Z E square divided by r square, and we equated this force equal to mv square divided by small r. That was Coulomb force was responsible for providing the centripetal force for orbiting the electron in the atom. But here the potential energy is given by the different formula because it is the hypothetical hydrogen atom. That means we cannot use the Coulomb formula for calculating the force, and this force cannot be equated with the centripetal force. So, what we need to do? We need to calculate the force for this type of the potential energy. This can be calculated by differentiating this relation with respect to r with the negative sign. We know the force in any conservative field is given by minus du by dr. So, let us calculate the force F equal to minus du by dr, and u equal to k log r, and differentiation of this log, that is a natural log r, equal to 1 upon r. So, this force is equal to minus k divided by small r, right. This is the force between the electron and nucleus, and we know this force is responsible for providing the required centripetal force. That means we can equate the magnitude of this force with mv square divided by small r. Let this equation is equation number 1. Now, let us move to the second rule of the Bohr's quantized theory or Bohr's atomic theory, and we know the angular momentum of the orbiting electron can be given by mvr equal to ns divided by 2 pi, right. Let us call this equation as equation number 2. Let us write equation number 1 and equation number 2 to the next page. And here we can observe we have the two unknowns, that is V and R, and we have the two equations. That means these two unknowns can be calculated. V, that is the speed of the electron, we can calculate for finding the kinetic energy of the orbiting electron. And radius of the nth Bohr orbit we can calculate if we calculate the value of small r. So, let us do one thing. Let us first calculate the value of small r. So, we can do one thing, we can square equation number 2 and divide this equation squared with first equation. this will be like this. Here we can observe this V square and V square will get cancelled, and this R and R will also get cancelled, right? And here will be m square and denominator is m, so only m will be left. And after rearranging, after solving, we will get the relation, that is m r square, this is m r square, this is equal to n square h square divided by 4 pi square and k. This is the relation. That means we can find the value of r square, and this r square equal to n square h square divided by 4 pi square k multiplication m. Now we can find the radius of nth Bohr orbit by under root of this value, right? This is r value. This is the radius of Bohr's nth orbit, right? Now let us find the kinetic energy. We know before calculating the kinetic energy, we can calculate total energy. We can write the total energy term. We know total energy is equal to summation of the kinetic energy and potential energy, right? So let us write kinetic energy and potential energy. And potential energy relation we have given, that is equal to k log r, right? And we know the kinetic energy here, this is mv square equal to k. So we can write 1 by 2 mv square equal to k by 2. So we got the kinetic energy. So here we can write this kinetic energy is equal to k by 2 and potential energy equal to k log r. Now we can substitute the value of r. This relation of r is in term of n. That means this total energy is in relation of n, that is the energy level, that is the energy corresponding to nth level. So this is the total energy corresponding to this hypothetical hydrogen atom. Now let us move to the next illustration. In this illustration, we need to find the angular momentum of an electron in Bohr's hydrogen atom whose energy is minus 13.6 electron volt, right? What is being asked? Angular momentum. We know electron orbit around the nucleus in the circular orbit. For calculating the angular momentum of any point object around circular path, or you can say circular orbit, we can use the formula mvr. But in this formula, in this problem, we are not given the velocity, that is v, we are not given the value of a small r, that is the radius of rotation. That means we cannot calculate the angular momentum by using the formula mvr. That means we should use some different approach. And we know the quantization formula for the angular momentum that was given by the Bohrs, that is equal to mvr equal to ns divided by 2 pi, right? That means from left hand side expression we cannot calculate the angular momentum, we should use the right hand side expression, that is ns divided by 2 pi, okay? And here we given the total energy and we have the relation for the total energy, that is equal to minus 13.6 z square divided by n square, and it is the hydrogen atom, that means z equal to 1, that means total energy equal to minus 13.6 divided by n square, right? So we can write this relation, that is E equal to minus 13.6 divided by n square, and here total energy is given as minus 3.4 electron volt. Here minus minus will get cancelled, we can get the value of n square equal to 4, and that means n equal to 2. Now we can substitute the value of n in this formula, that is 2s divided by 2 pi, and 2 and 2 will get cancelled, right? And here we get the result s divided by pi. This is the angular momentum corresponding to this energy, that is minus 13.6 electron volt, okay? Now let us move to the next illustration. In this illustration, we need to find the ratio of the ionization energy of the Bohr's hydrogen atom and doubly ionized lithium ion, right? This one. And we know the total energy of hydrogen like atom. We have the formula, that is equal to minus 13.6 Z square divided by n square, and this energy is always in electron volt. So, let us write this expression, this one, right. And we know that ionization energy is the energy required to eject the electron from n equal to 1 to n equal to infinite. That is, for removing the electron from ground state to out of the atom, that is the minimum energy required is the ionization energy. That means, we need to find the difference of the energy corresponding to n equal to infinite or n equal to 1, right. So, we can write ionization energy equal to E 1 to infinite, right, that is equal to E infinite minus E 1. We know E infinite equal to 0, just move the electron outside the atom. So, we should write E infinite equal to 0 and E 1 equal to minus 13.6 Z square divided by 1 square. So, let us write this equal to 0 minus E 1. Now, we can write this relation, that is minus 13.6 Z square divided by 1 square, right. This one minus minus will be positive. This is the energy required. We can write now this is equal to 13.6 Z square electron volt, right. Now, we can say it is nothing but the magnitude of the energy at the ground state. We can say ionization energy is nothing but it is the magnitude of the energy of the atom at the ground state. This is the energy at the ground state. Now, we can find the ratio. We need to find the ratio of the ionization energy of the Bohr's hydrogen atom and doubly ionized lithium ion. We know this energy is proportional to Z square. So, here we can write E ionization for the hydrogen divided by E ionization for the lithium, that is equal to Z square for the hydrogen divided by Z square for the lithium. So, let us write this relation now, right, and we know Z equal to 1 for the hydrogen and for the lithium plus this value is 3. So, this is 1 divided by 3 square and this is 1 divided by 9. So, this is the required ratio. Now, let us move to the next illustration. In next illustration, we need to determine the minimum wavelength of photon that cause ionization of helium ion, right. And we know the total energy of hydrogen like atom. We can express the total energy with the formula minus 13.6 Z square divided by n square, this formula. And we also know the definition of the ionization energy. It is the energy required to eject the electron from n equal to 1 to n equal to infinite. That is the minimum energy required for removing the electron at ground state to out of the atom, right. This energy is the ionization energy. That means, we can write ionization energy is equal to E infinite minus E 1, E infinite equal to 0. That means, ionization energy equal to minus of E 1 and E 1 is a negative quantity. If we substitute n equal to 1, this is the negative quantity. That means, the magnitude of the energy at the ground state is the ionization energy, right. Now, let us write the energy corresponding to the ground state. That means, we need to substitute n equal to 1 in this expression. So, let us write n equal to 1 and here we need to calculate for helium ion. So, Z equal to 2. So, let us substitute n equal to 1 and Z equal to 2. Let us calculate E1, that is magnitude of E1. Let us calculate the magnitude here. So, it will be equal to 13.6 2 square divided by 1 square, right, and this value will be 13.6 multiplied by 4. This is equal to 54.4 electron volt. This is the magnitude of the energy at ground state for helium ion, right, this type of the helium ion. And we know the energy of the photon is given by Sc divided by lambda, and this energy is required is 54.4 electron volt. That means this energy, that the magnitude of E1 should be equal to Sc divided by lambda, right. To ionize the helium ion should require this much energy. That means E1 magnitude equal to E, that is equal to Sc divided by lambda. And we know this Sc is a fixed value, and we have the shortcut formula for calculating the wavelength. If we express the energy in electron volt and lambda in the angstrom, we can write this lambda equal to 12400 divided by E in electron volt. By this formula we can write. Now we can substitute the value of E, that is a 54.4. So it is equal to 12400 divided by 54.4. After calculation, this is equal to 228 angstrom. So this is the wavelength, that is the minimum wavelength required for ionization of the helium ion. Now let us move to the next problem.